In order to do example number 4, where we need to show that 3 to the n minus 1 is divisible by 2 for all values of n, one of the things that we need to look at is our definitions. When it says something like divisible by 2, that means we're talking about an even number. So we got to show that this is an even number. One of the things that we also need to remember that if we have 2n, that is an even number. If we subtract 1, then we have an odd number. This also occurs if we add 1. Either way, for us, because it looks more like what we have in our problem, we're going to talk about the 2n minus 1 being an odd number. So essentially what we need to do is take a look at our 3n and kind of think about whether this is an even or an odd number. And we kind of alluded to this in our review, but let's take a little bit more about 3 times 3. That's when n is equal to 2. We can see that we get 9. But remember, that is an odd number, 2 to the n, 2n minus 1 times 2n minus 1, two odd numbers. If I do FOIL, I get 4n squared. I get plus 1. I get negative 2n, and another negative 2 is a negative 4n. We can clearly see that this is going to be an even number, and this is going to be an even number. So if I have two even numbers and I subtract them, my result is also an even number. And when I add, so this is going to be an even number, and when I add 1, it's going to become an odd number. So the question is that's true, then if I have 3 times 3 times 3, which is 27, also odd, notice that these two were an odd number. So we're going to get an odd number. And now we're going to multiply it times 3, which is also known as an odd number. And we get the exact same thing that we had, and we realize that the result will also be an odd number. So we're going to use this idea in order to prove our example. So let's begin our notes for page 118. One of the very first things we need to do is V1, which means we need to verify it when n is equal to 1. So when 3 to the 1 power minus 1, that becomes 3 minus 1, which is equal to 2, and we can see that that is divisible by 2. The next thing we need to do is sit. That means we say it's true when n is equal to k. So we're going to say 3 to the k power minus 1 is equal to an even number, or a number that's divisible by 2. The last thing we need to do is prove that it's true for n is equal to k plus 1. So we're going to prove that 3 to the k plus 1 minus 1 is an even number. So that's what we're going to prove. So just like we did in the previous examples, one of the things we're going to do is we're going to start with what we know. We know that 3 to the k minus 1 is an even number. So what happens then if I multiply both sides by 3? What we get on this side over here is that we have an even number times 3. Well, think about that. An even number is 2. 2 times 3 is 6. If I do 4, 4 times 3 is 12. We're going to get an even number over here on this side. So let's see what happens on the other side. On the other side, when I'm multiplying, I'm going to get 3 to the k plus 1. Remember, I'm just doing our distributive property. When I multiply these two, I add my two exponents. Minus 3, because I am doing my distributive property, and we say that that equals to an even number. Let's rewrite this minus 3. So if I write this to 3 to the k plus 1 minus 1 minus 2, that's just a fancy way of writing the minus 3, and we say that's equal to an even number. We're going to add 2 to both sides. Notice on this side, we're going to get an even number, because an even number plus an even number is even. So that's gone. And notice we have what we were looking for, that 3 to the k plus 1 minus 1 is an even number. So therefore we have proven that 3 to the n minus 1 is divisible by 2 for all numbers of n. Let's do example number 5. So we're going to start off with V1. V1 is when we verify when n is equal to 1. So it just means I get our first term. And we're going to see if that's true, that it equals to 1 over 2 times 1 plus 1. On this side we would have 2 plus 1, which is equal to 1/3. And if we look on the other side, that also equals to 1/3. So we have done the verification. Then we're going to do sit. That means we're going to say it's true when n is equal to k. So I'm going to have my series of 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7. And we're going to continue that until we get to the kth term, which is 1 over 2k minus 1 times 2k plus 1. And we say that that's equal to k over 2k plus 1. So we just said that it was true. So now we need to go to step 3, which is we need to prove that it's true. So let's first write down what we need to prove. We need to prove that 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 and all of these guys. The kth term is 2k minus 1, 2k plus 1. Well, now we need to add one more term because remember we're trying to show that this is true when n is equal to k plus 1. So one more term would get us to 1 over 2. So instead of putting k, I'm going to put k plus 1 minus 1. That's the first parentheses. The second parentheses would be 2k plus 1 plus 1. And we want to show that this is the same thing as k plus 1 over 2k plus 1 plus 1. So let's first start off with what we do know. What we do know is that from here all the way to here is exactly what we said in the sit portion, that this is equal to k over 2k plus 1. That's what we have up here. So we still need to add 1 over, so let's try to simplify some of this. So I'm going to have my distributive property will give me 2k. It will give me plus 2 minus 1, so that's a plus 1. The other parentheses will give me 2k. And then 2 plus 1, which is plus 3. So the question is, does this equal to k plus 1 over, and I'm going to simplify that portion, so this is going to be 2k, and that's going to be 2 plus 1 is 3. So we want to see if this is true. So now we do a lot of algebra, but we can kind of see this, our review prepared us for this. We need the common denominator, so we're going to multiply the top by 2k plus 3 and the bottom by 2k plus 3. So when I do that distributive property at the top, I get 2k squared plus 3k. And I'm going to go on ahead and add the 1 from this fraction because everything is under the same denominator of 2k plus 3 and 2k plus 1. So let's see, we need to simplify this, and we're going to get the factored form at the top. So I'm going to get 2k and k. Factors of 1 are 1 and 1. I need to get 3k in the middle, so I need to get plus here and plus here. And our denominator is still 2k plus 3 over 2k plus 1. And we can see that these factor out, and we end up with k plus 1 over 2k plus 3. So yes, indeed, we have proven that this works for n is equal to k plus 1. So we can conclude that This is true for all n.